Hello everybody and welcome to CS 302 Online. So today we're going to keep talking about sorting. Last time we ended by talking about insertion sort. And insertion sort was the one that as you go through it, you go ahead and you start putting them in the right order. So you have sort of a kind of like two lists. You have a sorted list and an unsorted list, and you're kind of taking stuff from the unsorted list and putting them in the right spot. So, yeah. See if I could fix that. There we go. Okay. If we learn some of the sorts from previous classes, can we use code from when we learn it? Yes, you can, as long as it was code that you did, not code that you took from like a book or something. So, hold on. Give me a second. Why is this not? All right, there we go. Okay, so. All right. By the way, I would like to inform you all that the hardware from Sally, I don't need the headset actually, has been updated. And so we have a better Sally now. And that might have caused some issues if you try to log into Sally today. If you do when you have problems, I want to show you something here. You will get an error like this. Actually read the error, because the error tells you how to fix the problem. All you have to do is literally run the command that it says to run right here. I obviously removed some details from this. Where you see the X's, you will see your own account, but that's literally all you have to do. If you do that, it will clean up any issues that you have with the fingerprint. And this is because we have new hardware that is still trying to you're trying to connect to the old hardware per se, okay? So as long as you read this and do what it says, then you will be okay. So, yeah, okay. So we have a question. If it was code we made from interpreting pseudocode, would that count as our code? It depends, I suppose. It's kind of like up to the TAs to decide. But basically, that pseudocode that you got, it depends, because like, if it's pseudocode and you're literally like let's say they gave you the full algorithm, and you are interpreting, you're taking that algorithm and you're just basically converting it from code that is pseudocode to like C++ code, and it's pretty much a one-to-one match, then that is kind of crossing the line into you're just getting the answer online. You have to come up with your own solution. If the pseudocode is just kind of talking about the algorithm in the sense of how I'm going to show it to you today, for example, Quicksort, then that is okay. So there's a gray line that's kind of on a case-by-case basis. So I guess if you're still unsure, then you have to kind of show me what you have, or show the TAs, and then we can work with you on that. But if you did the code yourself, and it was just based on some basic concepts of sorting, like, selection sort, you have two lists, you take something from this and you put it in that list and so on, that's perfectly fine to do. I mean, there's only so many ways that you can actually do these sorting algorithms. So that's okay. And again, if you just took code from a book, though, then no, that's not okay. I mean, it wouldn't have been okay in the previous class either, technically speaking, right? Because that would be plagiarism. So, yes. Anyways, let's continue. And like I said, if you're still like unsure, then just contact me or the TAs in private, and we can look at the special instance of that. So, also the fact that, I mean, if your code was for like an array and then now you're doing it for a linked list, that's different enough that you should be okay anyways, because you're pretty much rewriting the code already. So it shouldn't really matter for like that situation. So, okay, so today we're going to talk about selection sort, merge sort, and quicksort. And I think if we get through all three of those today, then we're in good, we're good. But if we don't, then we still have Thursday to talk more about sorting. And then after that, we'll start trees. But the cutoff will be sorting for the exam. I will be releasing a worksheet today for sorting, and I guess stacks and queues, I suppose. That is also going to be very useful for the test, so make sure you do that. It's also for a grade, but make sure you do that. And that will kind of conclude what's in the first test. So let's get to it, so that maybe we can finish Quicksort today. All right, so selection sort. Selection sort is another of those kind of easy algorithms, but not really efficient. And so selection sort, I always confuse it with insertion sort because they're just kind of just both like meh algorithms. But one way to think about selection sort is like minimum sort, because the way it works is if you're sorting in non-descending order, which again I'll just call it ascending order, but if you're sorting in ascending order, what you do is you look at the entire list, find the smallest number in the list, take it out, and basically that's going to be the first number of your sorted list. And then you just keep doing that until you finish. So let's go ahead and start plugging some numbers. So let me take my watch out here. So if it was class, I would just tell you guys to blur out numbers, but I'll just randomly pick numbers here. 5, 8, 1, 3, 2, 2. Why not? Might as well have duplicates, but hey, let's add them together. Or here, let's put a 1. There we go, duplicate. And 9. Okay? Sure. All right. So what you're going to do is, yet again, you have to think about it in terms of like two sort of subarrays. You have the unsorted subarray, and then you have like a sorted one. Okay, so this is unsorted, and this is sorted. Okay, and again, just to make sure we're on the same page, this is selection sort. Okay, so selection sort. What you do is you're going to put it, in a loop basically, and scan all of these items and keep track of the smallest number you've looked at. So I'm going to make a little square here that's going to represent the minimum of that iteration. So when you start, all you got to do is just copy the first number, because I mean that's the first thing you see is going to be the smallest thing you've seen so far, right? Once you have that in there, you're going to compare that with the rest of the array and identify if there's anything smaller. Okay, so you look at this, and really what you're keeping here is more of like the index of the location of the minimum, I suppose. You're not really keeping a copy, so I guess I'll put that instead. So really you're just keeping the location, which in this case is index 0, right? Array started 0. And the reason why is because it's not enough just to know what the smallest number is, but you want to know where it's at. So by having the index, you can do that. So then you look at the 8 and you check if 8 is smaller than 5, which is not. And again, we're doing ascending order, but if you were doing descending order, you would just flip the algorithm backwards, okay? Next, we're looking at 1. 1 is indeed smaller than 5, so we have found a newer minimum, right? And that's at index 2. So we keep track of that. We go ahead and look at the 3. 3 is not smaller than 1. 2 is not smaller than 1. 1 is not smaller than 1 technically because they're equal, so that's okay. Just keep the same one. This is important, right? Because here's the thing. The way I'm asking the question is our current minimum, or I guess better yet said, is what we're looking at, which is an index, smaller than our current minimum. Okay, that's the question that we are asking in code. Because that way, it's only going to get replaced the index if it is smaller than. If it's equal, such as the case of here with the duplicate, it will not get replaced. That's a good thing, because in this case, we want to make sure that the first one appears before the second one, because there's no reason to make this an unstable sorting algorithm when it can be stable by just respecting this tiny rule. Okay, so yes, selection sort is a stable sort algorithm as long as you follow that simple tracker, right? If you flip this around and you basically make the case where they're equal, where it replaces it, then it will not be stable, and it's unnecessary. So in fact, if you make it even slower, because you got to do the swap when you don't need to. So next you go to the 9. The 9 is not smaller than the current minimum. So now you have finished one iteration of the algorithm. Okay, you looked through the n items and you found the minimum, which was at location index 2. Cool. That is the smallest number in the list so far. What you're going to do now is you are going to keep track of that by putting it on the sorted subarray. Okay, so you're going to put that here. Now, I'm going to show you the simple way of doing this, but then I'm going to make it slightly harder because you can do this as an in-place sorting algorithm. Very easily to do, actually. But I feel like if I do it from the start like that, you might get a little bit confused. So for now, we're not going to make it in place, which means I'm making a brand new array, which I know how big to allocate it because it's going to be the same size as the original one. So if this first one is of size n, the second one is of size n, and I'm going to be starting to fill it in. And what I'm going to do with the old one is, once I go ahead and use that up, I can delete that. Now, deleting is an expensive operation, so you can go ahead and put in like an artificially really, really big number so that it never gets picked again. Or just have your array actually be an object when there's two member variables. One of them is the actual item, and the other one is a Boolean that says whether it has been used or not unused. There's a lot of ways to do this, okay? But ultimately, the easiest way is the second way that I'm going to show you. So for now, just bear with me as we kind of understand the algorithm first before we do it in a practical way. Okay, cool. So we can go ahead and sort of mark this as done so we don't ever look at that again. Okay? So then you run the algorithm again. So you start by saying that index 0 is indeed the smallest thing that we've seen so far, which is 5. And then you go to 8, which is not smaller. 3 is smaller than 5, so technically speaking, that gets replaced. So now you have here index 3. And then 2 is smaller, so index 4 gets replaced. And then yet again for 5, because that is the location of the smallest number so that we have now, which is another 1. And then when you finish that, you see that the index of 5 is left there. So that's what you're going to put there in your sorted one, and you mark that as done. Okay, run it again. Again, here the minimum is going to be set to index 0 because it's the first thing that we see, but then it's going to get updated to index 3 when we compare it with the number 3, which happens to be in index 3. But it's going to get replaced by index 4 because 2 is indeed smaller than 3. Okay, and then it doesn't get updated again because 9 is bigger. Okay, so now we found this next smallest, which is 2. So you put it here, and this is pretty much it. That's all there's to it, to the algorithm. The next time you run, you'll get the next smallest one, which is going to be 3. And then from there, you're going to get the 5, and then the 8, and then the 9, and then you're going to be done. Okay? So that's pretty much selection sort. Now, let me show you the way that you'd actually would do it in practice. Because there's no need to, there's actually a very simple way of doing this without having to keep track of whether something is used or unused, or even, again, to make it in order. So let's actually use the same numbers. So let me just copy paste this here, and then let me just write them in. 5, 8, 1, 3, 2, 1, 9. Okay, so it turns out that there's a very, very easy way of doing this in place. Okay, so now we're thinking code, basically. We have our array that we're trying to sort. Okay, get rid of this. So what we're going to do is we're going to start the same way that we did, but we're going to keep sort of an index at the start of the array. And you might be thinking, well, the start's not going to change. Well, you just wait and see. Okay, so we have sort of an index that currently has the value of 0. Okay, here, let me write the indices for these. 2, 3, 4, 5, 6. Okay, so now we're still going to have our minimum index sort of integer that's going to keep track of the smallest number that we've seen so far. But you'll see what happens here. Okay, so when we start, you set it to the initial, you basically copy the contents of the start. So you said whatever start has is what min is going to have. So right now start has 0, so you're going to copy over that to min index, okay? From there, you're going to increase this by 1 every single time and compare that value with what you currently have in minimum index. Yet again, following the same rule as before. That is what we're looking at, is AR sub I smaller than our current minimum. So is AR sub I smaller than AR min index. Okay? And if it is, then we go ahead and we replace it. So min index is going to get I. Okay, that's pretty much all there's to it. I'll put it down here. So as we run this, we will see that min index is going to again have the value of 2 in it. And then the full iteration is going to finish. When it finishes, and as you can think about this, is 2 for loops. The inner loop is going to run basically n times, and then the outer loop is going to run 1 time less by starting by running n times, and then n minus 1, n minus 2, n minus 3, and so on. Reason being is because when we finish that first iteration, what you're going to do is you're going to swap the indices of start and min index, the constants of the indices. So essentially, you're going to swap AR sub 0 with AR sub 2, okay? So what that means is I'm going to take 5 and the 1, and they are going to be swapped. After you do that, increase start by 1, which means it's going to go from 0 to 1, okay? When that is done, run another iteration of the algorithm. What was the first thing that we did? We copy start into min index. So we copy 1 into 1 now, this time around, okay? So then we go through, and right now the minimum is 8. So when we get to 5, that is a new smaller number. So this gets replaced with 2, but that's going to get yet again replaced when we get to index 3, yet again replaced when we get to index 4, yet again replaced when we get to index 5, because that's the smallest one, and then it's going to stay like that. Cool. We finish the iteration. What do? We swap start and min index contents. So in this case, we're swapping AR1 with AR5. So in this case, it means put the 8 that we have here over here, and then put the 1 over here. And then we increase start by 1 again. Okay? So that's pretty much the algorithm. I'm going to run it a little bit quicker now so we can finish through this, but that's pretty much the way you would implement this in practice. And as you can see, it's sort of keeping sort of the sorted section and the unsorted section, because right now this is sort of the sorted part and this is the unsorted part. And it's sort of building it as it goes. So now we have 2, and we are going to be looking at that 2, which have, first of all, copy it into min index here. So we got 2 here, which is currently a 5, but then it's going to get replaced with a 4 because the 2 is the smallest number, and then they're going to get swapped, 2 and 4. So basically 5 and 2 are going to change locations here, like that. And then we're going to increase start to 3, copy over that to min index 3, and then run it again. Basically, in this scenario, nothing is going to ever update min index 3 because neither 4, index 5, or index 6 have a smaller number than what the index of 3 has, which is a 3. So in this case, no update gets made, and when it finishes, we swap them. Now in this scenario here, 3 gets swapped with 3, right? Which means that no change happens, right? I'm swapping the same location with the same location. That's perfectly fine, not a problem. Then this gets incremented to 4. So we copy over the 4 here. So as you can see, that is not some sort of bug that's going to break our algorithm. You can swap with yourself. It might seem inefficient, but it's okay. It just makes the code a lot easier. I mean, you can put an if statement that checks every single time if they're the same. That's going to be slower than swapping with yourself, to be honest with you. So anyways, same thing's actually happening here with the index 4. It's never going to get updated. It's going to swap with itself, and then eventually start is going to get 5, and then that's going to be copied over, and yet again, nothing's going to happen. You still got to keep going, though. You might be thinking, can I just do a little like a, because it happened here, the scenario that whenever like we didn't have to swap, it always remained that way. That is not always the case. Like if 8 and 9 were in a different location, we would have had the 3 and the 5 basically not change anywhere, but that doesn't mean we're done. So we can't take a shortcut there and say that if the start and the minimum are the same and there's no swap needed, then we're done. No, you can't do that. With this algorithm, you have to run all the way until the last item. Okay, when you have one item left in the unsorted section, then yes, you can assume that it's already in the right location, but that's just saving, one time, so it's irrelevant. So that's pretty much the selection sort algorithm for you. From here, let's talk a little bit about the asymptotic complexity of this. So as you can see, there's no real way to make this more efficient. So it's always going to run basically n squared times. So this is going to be O of n squared. But also, I don't have this written down here, but I'm pretty sure by memory, it also has an omega of n squared, because there's no way to check if you're done until you run the entire thing. You're still going to check everything. You're going to see that nothing swaps. Then you're going to go to the +1. You're going to still check everything and nothing swaps and go +1 again. So you're always going to run it n squared. Even if I gave you the list that's already sorted, doesn't make a difference. It's still going to run n squared. The auxiliary space, so the extra space that this needs to run, is just O of 1 though, because you just need that swap variable. Although I guess suppose you technically need an index for the start and the min, but whatever, it's just constant time. So that's one good thing about that. The thing I have written here that I would want to point out is what's good about selection sort. I mean, it's really bad. It's always n squared. You know, at least bubble sort can be like O of omega of n or something like that. But the good thing about selection sort is that it never makes more than O of n swaps. Okay? So the number of swaps that you're making, which by that I'm saying that the number of times that I have to call my swap function, is only going to be the size of the list. So in this case, this list is of size 7. We have 7 items in it. So there's only 7 swaps that have to be made. So there's a lot of comparisons to identify what the smallest number is, but actual swapping, there's only 7 swaps. So that can be useful when the highest concern you have when you're working with a list would be memory writes. So I guess if you have a piece of memory that's very old or very slow to write on, like I guess in 219 when they talk about different memories like ROMs and the FPGAs and things like that, if I remember correctly, and I mean I did teach it in the summer, but it kind of went away now. There is some kind of memory that you can write to, but it's super slow to write to. I forgot which one it is. You have to like heat the thing to make it write, and it actually takes a considerable amount of time. So suppose if that was the biggest concern, or maybe like it wore out very quickly, I suppose, like memory writes wore the memory out very quickly, then selection sort. Yes, it's going to be super slow, like super slow. O n squared is pretty slow, but hey, if you prioritize the memory not being overused, then this could be a solution for you. Okay? So I'm trying to think if there's anything else I want to say about stability. Like I said, this can be made stable, relatively easy. This version up here was very easily to see stable. This version, when we do the swapping, I'm trying to think if you could run into problems with it not being stable, but I think you'd be okay. All right, so any questions on selection sort before we move on to merge sort? Okay, no questions. That's a good sign, I suppose. And again, I mean, selection sort is pretty easy. So merge sort is going to be the first of the algorithms. I frankly find merge sort to be very trivial too, but it's going to be the first of the algorithms that's actually quite efficient because it's going to be fast. Not the fastest, but up there. Okay, so this one's good. I see some people are redeeming extra credit already. That's impressive, most impressive. So go ahead and send me on Discord your who you are so that I can give the points to the right person, because you know some of you have nicknames which are like anonymous, so I have no idea who you are. So let me know, otherwise I don't know who to award it to. Okay, so yeah, anyways, merge sort. Let me go ahead and come up with another list here. So actually, why don't we use the same list? Damn it, I gotta copy it from the nasty list again. I might add a couple of numbers to this though, because I might want it to be slightly bigger. Actually, no, that's a decent size. Big examples don't necessarily mean better examples. Okay, so we still got our list, but this time we are going to use merge sort. So merge sort is a divide and conquer algorithm. And by that I mean that we are, instead of trying to tackle the list as a whole, we are going to divide it into smaller pieces that we can more easily manage. And so merge sort, as the name implies, involves a lot of merging. What we're going to do for merge sort, you can think of it as a two-step process. First, we're going to split this list into smaller pieces, and they're going to get small enough that each piece is going to be a single item. Once we have split the list into these small pieces, we're going to slowly merge it back together. And as we are merging the pieces together, we are going to basically combine those pieces, which I guess is another word for merge. And we are going to combine them or merge them in the correct order. Okay? One of the beauties of merge sort is that it's very easy to parallelize. I believe it's called an embarrassingly parallelizable algorithm or something like that. They'll talk about that in 370. So it's a great algorithm for that. It's very, very fast. So let's start. We consider our list, and I suppose I will copy before I do something to this. Let me copy it one more time, since I will want to use this list for Quicksort when we do over that. Might as well use the same list. So what we're going to do is we are going to, and I'm just going to go over the conceptual overview of this before we even think about pseudocode or anything, okay? What we're going to do is we're going to take this list and we're going to split it in half, okay? So how do we split it in half if it's an uneven amount of numbers? Well, it doesn't really matter, to be honest with you. There's 7 items here. You could split like 3 here and 4 here, or you could split 4 here and 3 here. That's not going to matter as long as, frankly, you are consistent. And even if you weren't, it doesn't really matter that much. I guess if you were parallelizing the algorithm, it might, but probably not either, frankly. So yeah, anyways, whatever. Just commit to one way and don't get confused in the test. Make it easy for the TAs. So yeah, let's split it like that. So the first 4 items are going to go here, 5, 8, 1, 3. And then over here, we're going to have 2, 1, 9. Okay? Cool. What do we do now? The exact same thing. We keep splitting it until we get to individual items. So in this scenario here, we're going to split this into a list of 5 and 8 and 1 and 3. And here again, it's uneven. So we're going to put 2, 1 here and then 9 here. We still got to split it one more time, technically. We split 5 and 8 into 5 and 8 into like individual lists of size 1s. 2, 1 gets split. This one, we don't split anymore because it's individual. So we just kind of bring it down. Okay, that's just visually. But algorithmically, nothing happens at that point. Okay, so now we have split our list into a bunch of individual integers. Okay, of course, this doesn't have to be integers, it could be anything, but we're using integer. That's the sort of the divide part of merge sort. Now comes the merge part, okay? So what we're going to do for the merge part is we are going to take all of the smaller sublists here in this tree, by the way, which is kind of a precursor of when we talk about trees in a couple of weeks. What we're doing is we are merging them back together in the correct order that we want, which in this case will be ascending order, but it could be descending order potentially, okay? In fact, no, we'll do ascending order, but maybe I can do it again with descending order really fast afterwards. So in this case, the first 2 things that we're going to merge, maybe I'll change colors, why not, is we're going to merge the 5 and the 8. And the way we're going to do it is we are going to create a new array of size 2, which contains both of these elements in it in a sorted manner. How do you know which one you pick first? Well, you look at them and you see which one's smaller, and then you put that one first, and then you put the second one, okay? That's pretty much it. This will make more sense when we start merging larger lists, but really we are just kind of putting everything back together now in the right order. This happens to be in the right order already, so that's kind of nice. This one is not, we see that the 1 is smaller than 2, so that goes in first, and then the 2 goes in. The 9, at this point, we're not really merging it back with anything because it happened to kind of have this extra thing here. So we're just going to leave it like that, okay? All right, so now we have potentially merged a bunch of our individual lists into lists of size 2. But each of these individual lists are sorted, right? All of them, look at them. They're all sorted. Like 5 and 8 is sorted, 1 and 3 is sorted, 1 and 2 are sorted. Now, I'm not saying like combined they're sorted, but individually the size of 2 are sorted, and then the single 1 is technically sorted because it's alone. So now we're going to sort of repeat this by merging larger lists. So these two are going to get merged, and then these two are going to get merged. So this is where the fun begins, I would say. When you're merging lists of bigger sizes, essentially, what we're going to do, and I'm going to kind of do it on the side here. So we got 5 and 8 on one list, and then we got 1 and 3 in the other list. What you're going to do is you're going to keep track of 2 indices, which are initially pointing to the first item of the sublists. So in this case, we'll say, well, I guess we'll call this like I and J or something, okay? So I and J are currently 0. And we know that S, being our size, is equal to 2 or whatever, okay? So what we're doing is we are comparing these subarrays, which I guess I'll call like AR1 and AR2. We are comparing the index at that location, so AR1 sub I and AR2 sub J. We are comparing them and seeing which one is smaller. And we see that 1 is smaller than 5. So we are going to create a brand new array, which is going to be the merged array, which is going to be of size, because if you need to know how big to make it, just look at both of them. Don't just look at one of them and multiply it times 2, because you could be merging something with like, when we get later here, we're going to be merging 3 things here instead of 4. So you figure out how big both subarrays are and allocate memory of that size. So we know that our final array is going to contain 4 items. The one you're going to put in here is going to match the smallest one of the 2. So in this case, it's going to be 1. Why? Because 1 is smaller than 5. Now, what you're going to do is you're going to increase J plus 1, which is going to move it to the next item in the list here. Okay? You move, after you copy something over, you increase it by 1. It's sort of like together. You know, if you figure out that the 1 on the J side is smaller than the 5 on the I side, copy over that to the combined array and then increase it by 1, okay? Next, you're gonna again compare AR sub I and AR sub J, okay? They're different, AR1 and AR2 technically. Again, 3 is smaller than 5, so we're gonna copy 3 over and then increase it by 1. But now it's, what does J have? J has 2, right? Because it started at 0, 1, and then 2. Because J is equal to S, that means that one of the 2 arrays that you are trying to copy, you have completely covered and it's done. At that point, this is a sign, and this is sort of a shortcut, that you can just copy and paste the remainder of the other array into the list. So literally just copy and paste 5 and 8, okay? That will happen typically where one of the sublists will finish and then you copy the other one. Now, you might be asking like, why does this work or something? Think about it for a second. Like, we were comparing by starting at pointing, by pointing to the beginning of both. And the fact that one of them finished must mean that even the first number of this one is bigger than the one over here, right? So it must mean that if we got to here on one array, but we are still pointing to something before the last one of this array, it means that clearly this whole thing is smaller than this number, and anything after this is bigger, because remember, these sublists are already sorted. They are already sorted, and they are 1 and 3, 5 and 8. So the fact that we finish here and we're still looking at the 5 means that anything after the 5 can just be put there because it's going to be sorted in the right place. So you might have to kind of think about that for a minute and just kind of see the light of why this is the case. But trust me that it will always work. So we went ahead and we merged the list. So now we have 1, 3, 5, and 8. We're going to do the same thing with the 1, 2, and 9. We started by looking at the 1 and the 9, and we see that the 1 is smaller, so we put that in the combined list. And then the 1 moves to the 2, and then when you're looking at the 2, you see that the 2 is smaller than the 9, so yet again that brings it down. Because we have finished the 1 and the 2 sublist, then the 9, which has not been finished, that list is going to be copied over, which just has 1 item in it, but if it had more, then those will be copied at the end or appended. So now we got here. Okay, let me go ahead and move this down so we have space. Next, we are going to just keep doing the same thing until we merge, until we have one list left. So right now we have two sublists again. These sublists are sorted. You can see 1, 2, 9, 3, 5, 8. But now we got to combine them, okay? So we got to merge them. So again, we'll start by pointing out at the beginning of both lists and then merge them together. So here's where you got to be a little bit careful, okay? If you want merge sort to be a stable sorting algorithm, then you got to make sure that if you have a duplicate like here, where you have 1 and 1, that you always take the left side first, okay? That will guarantee that this is a stable sorting algorithm. So in this case, while both ways will give you a sorted list, if you want it to be stable, you have to do it the way I'm saying, okay? So you take the 1 from the left side, okay? So now we're looking at 3 and 1. 1 is smaller than 3, so we're going to take the 1 down from there, and then we're going to shift this by 1 here, okay? We're looking at the 3 and the 2. The 2 is smaller than the 3, so therefore we are going to again copy over the 2 and shift this by 1, okay? As you can see, I would say pretty much every implementation of merge sort is not going to be in place. Frankly, if there's even a version of merge that's in place, it's just going to be way, way complicated, and it's not going to be stable. It's not going to be stable. So that's okay. That's why in the assignment, I make you do the linked list version of this. So anyway, now we're looking at 3 and 9. 3 is smaller than 9. We can't copy append an entire list because we're not done with either list. It's only after we're done. In this scenario here, we have kind of the worst possible scenario because, as you can see, no list is going to finish until we're basically done. So yeah, we're going to copy over the 3 now, and we're going to increase this by 1. 5 is smaller than 9, so we're going to copy over the 5, and then increase it by 1 again. So now we're looking at 8 and 9, so we're up to our last 2 items. 8 is still smaller than 9, so we're going to copy over the 9. Sorry, we're going to copy over the 8, and then increase it over. After that, we go out of bounds, which is the size. This is index 5 at this point, or sorry, 0, 1, 2, 3, 4, index 4, my bad, which is the size of the list. So that's how you know you stopped. At that point, append the remainder of the list, which happens to be just 1 item. So this is kind of like the worst case scenario of that. In the other cases, we had a nice case where we have to copy 2 things and save some time. This will be the worst possible scenario, okay? So now we have finished. We have our list sorted because now we don't have this to merge this with anything else. But perhaps this was actually a bigger tree, that maybe this was being merged with another whole tree. And in that case, you would do that merge there, okay? So that's pretty much how merge sort works. Here's the really cool thing about merge sort. If I had another list somewhere else that was already also sorted, I could merge them together to create an even, like a list that's sorted of both lists. So merge sort can be very useful when you have a bunch of different smaller lists that you're trying to put them together in a sorted manner. It's very efficient for that manner. Also, here's a really cool thing about merge sort. These trees get split in the beginning, right? Like the big list gets split into 2 completely independent trees that only get merged at the end. I don't need to have in main memory both trees at once. I can have one tree here and another tree there, load it into memory one at a time, do the sorting, write to memory, load the other one, do the sorting, write to memory. So there is something called polyphase merge sort, which they'll probably talk about in analysis of algorithms. But if not, you can just Google it on your own time. It's a slight variation of the merge sort algorithm that is focused at allowing you to sort really, really, really big files. So normally, you don't think about this when you sort something for like an assignment. You're sorting something, you load it in memory, and sure, it's slow if you're running bubble sort, but it's in main memory at least, right? Well, what if you're trying to sort like thousands of terabytes, or like a petabyte or something? That's not going to fit in main memory, right? In fact, gigabytes may not fit in main memory. If you're sorting like 100 gigs of data, you may not have enough main memory to do that. You might, we have a computer, that has 500 gigs of RAM, we used that at some point actually last semester for sorting Wikipedia. We were sorting all words in Wikipedia, and so that was a cool project that we were doing. But that was a situation where we actually needed to have that much memory so that we could sort using like a built-in sort function. But if we wanted to use something where we couldn't fit it in the main memory, we could have used polyphase merge sort. What polyphase merge sort will do is it'll load part of the list, sort that section, then load another part, sort that section, and now we have basically have a bunch of subsections that we're trying to sort. Well, here's the beauty of this. Think about how we did this algorithm. We start by having both of when we're doing that last merge, we have those indices pointing to the beginning of the list. You don't need to load the entire sublist in main memory to do the algorithm. I could load, like, let's say I can only have 4 pieces of memory, 4 numbers in main memory at a given time. Okay, I can load the first 2 of each list, and then as I figure out which is smaller and which is bigger to start building the final list, I can shift what I have loaded in memory like this way or this way as I go, right? So I suppose in this method, it would be first shifting the left one and then the right one. And so I can use this to only load parts of the list. And then of course, the stuff that I'm doing here, the final list, I'm also writing that to main memory, to hard drive. So the only parts that I need in main memory are smaller subsets of both lists. And as I go ahead and pull information from one of them and I draw to the end, I just load more. I preload it and I keep doing that. So polyphase merge sort is very, very, very good when you're trying to sort lots of data, okay? And then you can't have that in main memory. It's not as fast because, yes, loading stuff from hard drive is not fast, but it's might be the only way that you can sort this stuff. You can't sort this with bubble sort that way. I guess with bubble sort you can load pieces of memory, so I guess you could do that, but it would be way, way slower. And something like minimum sort or selection sort would be bad because you have to load the entire list to find the minimum, and then you got to load the entire list again. So you could load pieces, but it would still be pretty slow. So what is the time complexity of merge sort? Let's actually analyze this one because this is a good one to analyze. We start out by having an entire list of size n, right? But each of the layers are half of that size, approximately, plus or minus 1, right? Well, yeah, n or minus 1. So you're dividing it by half every time, and then when you're merging it, you're merging the halves back in. Because of that halving, hopefully that rings a bell with logarithm. And it turns out that this indeed does take n log n time. In the worst case, in the best case, I believe, and in any case, it's always the same. It's n log n. That's very good. That's better than n squared. If you have 10 items to sort, you got to do 100 comparisons with bubble sort, selection sort, or insertion sort in most cases. With this one, if you got 10 items, all you got to do is 10 times log of n, which is about 3, so about 30 comparisons. 30 comparisons versus 100 comparisons. Not bad. Let's do a bigger number, 100. 100 times 100? That's a pretty big number. Gotta put the number of zeros correct. So that's 10,000, right? With merge sort, it's going to be 100 times the log of 100, which is going to be what, like, I don't know, 2, 4, 8, 16, 32, 64, 128. So that's about 1, 2, 3, 4, 5, 6, 7. So about 7. I was thinking 8 in my head, so I was close enough. So about 700 comparisons, approximately under 700 comparisons, because it's going to be in between 6 and 7. So but you could take the ceiling function of that. So 700 comparisons. 700 comparisons versus 10,000 comparisons. Let's say each comparison takes 1 nanosecond. Okay? It's still relatively fast in both situations. But let's say a comparison takes 1 second. Now we're talking some serious business here. This is going to finish in like a day versus like a week, or something like that. If O and omega are the same, then theta is always the same, right? Yes, of course. Because remember that theta is in between O and omega. And if they're the same, then it's kind of sandwiched to the point that it becomes the same, right? So like if you have two lines and theta is supposed to be in between and it has space, then sure, it could be kind of wobbling in there. But if the lines are literally crushed to the point that they're the same line, then yes, this is crushed in between, right? So yeah. So anyways, I understand that n log n is a huge improvement over n squared, okay? The bigger you go, the bigger the improvement, okay? Go for a million numbers, and then basically a million squared compared to a million times like 20 million, okay? Way faster. So merge sort is one of the fastest algorithms, but it turns out that Quicksort or Timsort, which is a combination of merge sort and insertion sort, is a little bit faster than just pure merge sort. That's the one that libraries typically use, like in C++, Java, Python, and that kind of thing, when you call the sort function. So what else do I want to say about merge sort? I have a comparison on Canvas between merge and Quicksort, but I will talk about that once I talk about Quicksort. So let's see. I suppose when it comes to implementation, the best way to do this is to, again, don't try. I would highly discourage you from trying to use the same array. But you will definitely want it to be some sort of recursion for doing the same thing repeatedly. You could do everything iteratively, don't get me wrong, but it might make your life easier. I would check, if you want to see a sample code, which you can't copy off for the assignment, but you can use to kind of better understand the algorithm, go for Geeks for Geeks, and they have an example in C++, an implementation that's pretty well commented, so you can kind of see. Because we really don't have time for me to like write out the entire code for this. What I would like to write is the recurrence relation for this. The recurrence relation for this we have already seen. That's the recurrence relation for merge sort. And if we use the master theorem for that, if I remember correctly, I think A is 2 and then this is B, right? Maybe, I think. Hopefully I'm not flipping them. It doesn't matter though because they're equal, but either way, because remember it's like log, I think BA or AB, but in this case it's not going to matter because it's going to be log 2, so it's just going to be 1. And then for the D, it's going to be the power here, which is just 1, right? So D is going to be equal to 1. So in this case, 1 is equal to 1. So that is going to be one of the cases of the master theorem, which I believe is the case where you do something like n to the d log n. And so since d is equal to 1, you get n log n, okay? So that will be the master theorem of doing it. Where does the plus theta n come from? Okay, so we have to understand how the algorithm is running to figure that out. So how many columns are there going to be, or how many rows there are going to be to the algorithm? How many splits are there going to be? Well, it's going to be the half of the half of the half until we get it down to 1, right? So if you can see here, we have 1, 2, 3 plus the original 1. So the original list was 7, so we got about half of it, okay? And then we have, for the combination, is going to be basically the other half, okay? So the logarithm part is coming from the fact that the list is being split into halves. The theta n part is coming from the fact that we have that number of rows, basically. I think that's the best way to understand it. So I'm trying to think if there's a better way. Yeah, I think I'll stick with that for the explanation. Oh, they had an explanation on the on actually being resolved with the recurrence relation. Nope. Okay. Auxiliary space, you do need more space in this one because you're not making it in place, so you need at least a size of n array for that. It's not in place, but it is stable as long as you take the left before the right. And it is very convenient for linked lists. So yeah. Any questions on merge sort? I don't know what else to tell you without just like spending time coding, which I don't think is very beneficial for that one. I think it's better to focus that on Quicksort, which is the hard one. In merge sort, how are we updating the indices again for comparing the elements in the subarrays? So let me just give you an example. Let's say that we have two lists that are like 5, 1, 3, 4. I guess well, no, because it's going to be sorted at this point. So let's say we have 1, 5, 8, and we have 9, and then we have 2, 2, 8. I have issues coming up with random numbers here. 9. Wow. I'm trying to make it unique, but no success. So when you have the two sublists like this, both indices always point to the first item, which is index 0. What you do is you're looking at the two indices and you're picking the smallest one, and that's the one that you're copying over to your new array. So you're copying over the one here, and when you copy something, +1 your indices. Okay, so I++ essentially in code, and then compare again your I and your j. So we'll say this is I and this is j, and this is AR1 or AR left and AR right. Okay, and you're looking at AR1's I or AR1's j. And so in this case, the 2 is smaller than the 5, so you copy that one over to the new array, and then plus it. And then again, the 2 is smaller than the 5, so you copy that over here, and then plus it again. Now you're looking at a 5 and a 7. The 5 is smaller in this case, so that one we are going to copy over and plus. Now we're looking at 8 and 7. In this case, the 7 is smaller, so we go ahead and copy that over and then plus again. Now we're looking at 8 and 9. In this case, 8 is smaller, so we copy over that and then we plus it. Now we're looking at 9 and 9, in which case you take the left one so that you can keep it stable, and then plus it. When you plus it and you go out of bounds in the array size, so in this case it's a size 4, and you can see that now we're at index 4 here, because that would be technically outside of the array. When you see that I is equal to S, that's when you know that you finished one of the lists. What you do at that point is copy the remainder of the other list by copying whatever is an AR2 sub j in this case, plus anything after that, which in this case is nothing. It's just basically the, what the heck? It's just 1, 9, right? But let me give you an example where you would copy more things. So let's suppose you had an example like this: 1, 2, 3, and then the other one happened to be like 8, 9. Okay? 8, 9, 9, like that. So in this scenario, when you're looking at the indices, you start out by looking in the 1 and the 8. You copy the 1, then you plus it, so you copy the 2, and then the 3. So essentially, you got 1, 2, 3 here, and then you go out of bounds here. All right? So because S is equal, which in this case is 3, is equal to index 3 now. So at that point in time, you take the remainder of the list here and just append it like that. Okay, just copy it over manually. What if it was 2, 2, 7, 8? Would the 8 be inserted at the end? 2, 2, 7, 8. Let me see. So if this had been 2, 2, 7, 8 here, we would have copied all the way until, let's go back all the way until 5, okay? So at that point, we have this one pointing to, well, let's say we just copied the 5. So it was pointing to 5, and then this was pointing to 7, okay? So at that point, we copy over the 5, so we increase this by 1. So it goes over by 1 here to the 8. Now we're looking at a 7 and an 8. The 7 is smaller, so we copy over the 7. This moves to an 8 now. Now you're looking at 8, 8. But you copy the left 8 first so that it's stable. Both are wrong. Both are correct, by the way. We're just saying, if we can make an algorithm stable and it's not a big cost to us, it's better that way. Because it's more flexible for people that want to use it. So that's why it's preferred to make it stable. And when it's something as easy as just making sure you put your if statement in the right order, then it's worth leaving. So then this gets increased to the 9. Then we copy the other 8 because 8 is smaller than 9. And then this gets increased out of bounds, at which point copy everything left over, which would be the n9. So cool. Any other questions? Other special cases you want me to show you? Again, when you're getting to the combining stage, you will never have a situation where the sublists are not in order. Like, you will never have a case where it's like 2, 2, 7, 1. Like, that won't happen, because that means that something else would have messed up before. What's the worst case for merge sort? That's a good question, actually. I like that. So even though they're all n log n, what will be the one that is going to make us do the most swapping? And if I recall correctly, it is, I think it's descending order. I think it's descending order, because if you give it something like 5, 4, 3, 2, 1, eventually it's going to get split up into like 5, 4, 3, 2, 1, and then this gets split into 2 and 1. This gets split into 5, 4, and 3, and then this gets split into 5 and 4. So when it's combining here, it's doing 4 and 5, and then the 3 just kind of comes down, and then this here gets combined into 1 and 2. So there really isn't much happening there. This gets combined 3, 4, 5. So that's actually good here, because we don't need to do anything here. But then when we gotta combine these, we copy 1, 2. So no, it's not. I don't know. I think it would be like a spiraling situation. What you want for a worst case is where you can't append the remainder of the list, right? Like a situation where you basically have to compare all the numbers, and you basically are looking at the last number on both cases, is the worst case. A situation like this where, like, once I finish the 2 and they go to the 3, like out of bounds here, which means I can just copy over the entire list. It's an ideal case. So I can't think of a numerical example for the worst case, but I can tell you what it would look like. Like I said, it would look like this, where the numbers are so intertwined that you can't append the list, okay? That means that the last number of each list is potentially the last 2 numbers of the list. Yeah, so the 9 and the 8 you can see are the last numbers that are going to go in this list. And as long as one of each of those is in each list, you're not going to be able to skip steps here and append. So that's going to be the half-assed explanation as to that. I'll have to Google for more about that. But that's a really good question, though. I like that. Do I have anything written about that here? Sometimes I have like the worst cases written. And I mean, it makes sense that it's hard to figure out a worst case, because remember, it's always n log n, right? So like, naturally the algorithm doesn't really have a really bad scenario, because they always take about the same time. So it's harder in that situation. Quicksort is an easy one to give you the worst case. So let's talk about Quicksort then, I suppose. All right, so Quicksort is the one that freaks the students out usually. They think of that one as the hard algorithm, and the one that's like, oh no, I gotta memorize it. Quicksort, I will spend extra time on. So based on the time, we have 15 minutes left, so we're definitely not gonna finish fully Quicksort. But that's okay, because then we can spend the next class kind of going over more of it. But this one I'll actually do more like pseudocode, because again, this is a harder one. Merge sort you can kind of handle on your own at this point, but Quicksort, it's tricky. So with Quicksort, we're going to learn 2 methods of partitioning schemes, which are known as Horde's method, Horde with E, not Horde's method, I think. And there's also Lomuto's method. So we're gonna do both methods. Probably today we're only going to do Horde's method. Horde's method is the better one. It's faster. It's actually legitimately faster than Lomuto's method. But Lomuto's method is a little bit easier to understand. So for Lomuto's method, I actually found a really, really good video. Normally I would show the video in class, but I can't show it on the lecture because of copyright, I suppose. So I have a Canvas link, which I've always had, that links to it. It's called Quicksort Reference, and there's a video there. So I will go ahead and post a link to it on the chat here, so you can check it out in your own time, or go, like I said, to the to Canvas and find it. So there's one tiny mistake in that video, but he actually added it to the comments at some point. It's by no means is it something that like will confuse you. It's just the last step actually. But I would recommend you check that out before next class. That way, he'll do a better job of explaining that method than I will. Frankly, the reason I don't really know that method too well is because it's not the most efficient method. Hor's method is way better in all cases. I can still show you Lomuto's method, but like, you know, it's just, I have to think about it before I show you kind of thing. Like I have to like process it. It's like bubble sort and quicksort put together. So anyways, Hor's method just makes so much sense and it's like so much better. So that's what we're gonna kind of go with. So I have a bunch of numbers here. I can try and pick my own numbers, but I'm gonna go with these numbers because I think I had them the way I had them because then they show all possible cases. So I'm gonna go with that and see what happens. But also, actually, yeah, I also do want to do the same list again because I mean we've kind of done it so many times already. In fact, where's it at? Here it is. Actually, we could start with that list and then we'll do that one. Yeah, why not? So, before starting Quicksort, let me kind of explain to you the idea behind it, okay? So it's a divide and conquer algorithm, just like merge sort, but instead of trying to sort of do most of the work when you're merging things together, you're kind of going to do it on the splitting part, so like on the dividing part. So Quicksort does most of its work there. In fact, when you finish splitting it, you're kind of done. Think about it the right way. So the way it works is you take an array of information that you're trying to sort, and you're going to partition it into two subarrays. Whereas before we were just kind of splitting it right down the middle, what we're going to do here is we're going to pick arbitrarily one of the items in the array that we're working with, and we're going to call this item our pivot. And what we're doing is we're going to compare this pivot with all of the members of this array, and numbers that are smaller than this pivot are going to go on our left array. Numbers that are bigger than the pivot are going to go on the right array. Okay? And that's it. That's pretty much the algorithm. As long as you understand that much, you understand Quicksort. The rest of it is just trying to put the idea into code. That's all there's to it. So the way I'm going to first show you Quicksort is sort of the conceptual way that you would do it. But then next class, I am going to write some pseudocode and I'm going to show you how to do it like in practice, like very systematically. So we're going to be like one step close from basically just pure C++ code, okay? Because I want to make sure that you understand it. But I think if you understand it conceptually first, then the rest will make sense. Kind of like how we did selection sort. We were first going to show you conceptually and then show you how to do it in place, okay? So conceptually, what I'm going to do is I'm going to pick my pivot in this scenario as the last item of the list. Now, selecting the pivot is an art. And why is it an art? Because it makes or breaks Quicksort. Picking a good pivot makes the algorithm faster than merge sort. Picking a bad pivot makes the algorithm as slow as bubble sort. That's bad, right? Because I've been telling you Quicksort is faster than merge sort, but now you're like, whoa, wait a second. If I screw this up, it's going to be slower than bubble sort? Like, are you kidding me? No, I'm not. Maybe I'm exaggerating a little bit, but it's going to make it pretty slow. Almost as bad as bubble sort, okay? So it turns out that one of the best ways to pick a pivot is actually to pick it randomly. So we're just going to go with our feelings and just pick the last item to be the pivot. So in this case, it's going to be that 9. All right. So what I'm going to do is, since that is my pivot, I'm going to kind of put it in the middle here. And now I'm going to put the left and the right partitions. I'm going to call them left P and right P. Left partition and right partition. Okay. And what we're going to do is we're going to work our way from left to right and put things where they basically go. Again, This is not the way that you would code Quicksort, by no means, but this is so you understand the basics of it, okay? We'll go over the inner workings of how to actually code this and how the partitioning works properly next time. I just want you to understand the basics of it, okay? So, the 5 is the first number that we're looking at. We look at the 5 and we see if it's bigger or smaller than 9. 5 is smaller than 9, so you're going to put it on the left partition. Okay? Next, we're going to look at the 8. Oh, we're already hitting a... See, this is why I should have picked the other list, because this list is already going to show you a special scenario. It turns out that, guess what? All the numbers that we have here are smaller than 9. So, yeah. 8 is smaller than 9, 1 is smaller than 9, 3 is smaller than 9, they're all smaller than mine. So, fail. And this is why I should have picked the list of numbers that I had. But hey, no, this is good too, because I did want to show you this special scenario. We've already jumped into the bubble sort tier of Quicksort right now. The worst case scenario of Quicksort is when your pivot is actually the biggest number or the smallest number in that array. Because, as you can see here, we basically split the list into a empty list here, our pivot, and then the rest of the list. So, pretty problematic, I suppose. But as you said, but that's okay. It's okay. Whatever. We shall carry on. Okay? All right, cool. So now we're going to do the same thing here. We're going to split the remainder of the two sublists. So just kind of like merge sort. With the beauty of merge sort that I guess I really didn't emphasize, but I should, is that the left and the right trees are independent of each other, right? So here's the cool part. If you have multiple computers or multiple processors, you can go ahead and feed one side of the tree to one computer and then the other side to another computer. And they could be working separately in parallel, and then merge together to get the final list, right? So that would cut your time in half, essentially. Because right now, even though I wrote this nicely, you are going to have to go in some sort of sequence here. Like you're probably going to go in this sequence. Like you're going to run through this, merge this back, then go all the way here, merge this back, and then finally merge this together, then go here, split it, merge this, go back down, merge this, and then you're done, right? So you're kind of working your way through that in an interesting manner. You don't have to worry that because recursion takes care, but it's interesting. Parallel programming allows you to actually legitimately work in them at the same time. Quicksort is a little bit like that too, in that regards. But you'll see that more again when I actually show you the implementation in practice, okay? So anyways, going back to this now, back to Quicksort, we're going to do the same thing again. We're going to pick our pivot to be the last item, okay? We're going to say that lightning doesn't strike twice, even though it's going to strike twice here, pretty much, okay? We're going to say that, what are the odds that we're going to get the biggest or smallest number again? Which we happen to actually have the smallest number in this scenario, but it's okay. So I actually expected this not to be so unbalanced, so I'm going to have to kind of like scoot this over this way so we don't run out of space. But now we are doing the same thing. We are going to take our pivot as being kind of like the middle thing and then split it into two lists. So 5 and 8 are bigger than 1. 1 is the same size as 1, so put it on the left side. Otherwise, the algorithm may break. But also, it's not because we're trying to make it stable, because Quicksort, it's not stable. You can't really do much to avoid that. It is inevitable that it will be unstable. Okay, the 3 and the 2 are bigger than the 1. So again, it's not the worst case scenario here, but I would say it's like the second to worst case, because the ideal thing behind the pivot is that you want these lists to be balanced. Like you want them to be about the same size. This is totally not balanced, but we shall carry on. All right. Same thing. We're going to pick that to be our pivot, which is the last item. So we're going to put the 2 now, and then we're going to start work our way. So 5 is bigger than 2, so we put it on this side. 8 is bigger than 2, so we put it on this side. 3 is bigger than 2, so we put it on this side, and we got memed again, essentially, because we also had the worst case. Wow. Well, I guess I won't have to show you what the worst case of Quicksort is, because you got to see it in the live. So yeah, literally, like I'm not even kidding. Like, oh my God, it's happening again. We got 5 and 8 over here, and then literally, well, in this case, it's always going to be that scenario when you have only 2 items left. But yeah, okay. So anyways, we have partitioned the list. Here's the cool thing about this when it comes to merging. The list is already sorted now. You don't quite see it, but it's sorted. Here's how you go ahead and build the list at this point, okay? I mean, hey, when you pick a good pivot, this thing is better, okay? I do like merge sort better. It's more elegant, and like Tim sort, which is the most efficient, does use merge sort and I believe selection sort or insertion sort. I can't remember which of the two. I think it's insertion sort, but hey, we just picked a bad pivot. What can I say? So okay. Now that the list is like split, shouldn't the 5 be on the left for the last branch? Oh, yeah, you're right. Thank you. Good catch on that. Yep. I was just so triggered at the pivot choosing that I didn't see that. So anyways, okay. So this list is actually sorted. You don't really see it here because of the way I drew the tree, but you would have seen it if I did it like the algorithmic way in place and whatnot. But just look at the pivots and the list is sorted. Okay? So you have, when we talk about traversals, this will make more sense. But what you do is, this is, I suppose, a in order traversal technically. So the 1 goes first because it's this pivot, and then the 2 goes then because it's another pivot. Here's another pivot. This is the part where you kind of understand how traversals work, because this actually goes before this, and then finally you get to the 9. Okay? So if I was to draw how this goes, it would go like this. Oh, and technically speaking, this is another pivot, so that would have gone first actually. So the way you would do this is you would go this way, here, there's nothing there, so technically there, and then there's nothing here, so you go here, and then you go to the 5, nothing there, then you go here, and then you go all the way back up, hit the 9, and then go this way. Okay, let me draw that again to make sure I make it clear. So you start out by going, technically speaking, from the true, you go all the way here, print if there's anything here, print this out, so you get 1 out, put it, print this, get output it, print the 2, print the 3, print the 5, print the 8, goes all the way back up, prints 9, and then if there was something here, then you would print it, okay? That's actually what it would look like. But again, that is more of understanding how trees work. We will talk about it in multiple weeks, okay? So, yeah, that's Quicksort for you. We looked at the edge case, so I guess might as well for the last 2 minutes talk about that, and then next time we'll do that example, which I'm assuming I had because I knew that it would be nicer. I can already see it because the 11 is kind of in betweenish a little bit. Why not use the mean of the data as a pivot? That's very good critical thinking. I like that, and I wish that you were right on that as much as you're passionate about it. But the fact of the matter is that it will not work, because here's the thing. Quicksort, in the best case scenario, is going to take n log n time, okay? In the worst case scenario, it takes n squared time. Here's the thing. To compute the average, the mean of a list, requires you to look at all of the numbers of the list, add them together, figure out what the mean is, and then identify which of those numbers is closest to the mean. That requires you to look at the list n times, which means you are not to do that for every single one of them. So that would defeat the purpose and make this always take n squared time. So that's a no-go. But it was a very, very good idea. So, yes. Anyways, choosing the pivot, like I said, is an art, because you are correct in thinking that the median number, not the mean, but the median would be the best number for the pivot. right? Because the median guarantees that it's literally the middle number in terms of quantity. So that means that we're gonna have the exact same numbers on the left than the right, plus or minus 1 because of, you know, odd or even. However, identifying the median would require us looking at the entire list, which would slow down the algorithm too much. Okay? So that is why picking randomly is a pretty good way to sort of, because I mean, mathematically speaking, if you pick a number at random from a list, you have decent odds of it actually being somewhere in the middle, right? So that's why picking at random is usually best. But as we saw here, we won the lottery essentially. In this case, it was the loser's lottery, but we won the lottery. Okay, we got hit by lightning essentially. So yes. So that's where I'll stop. I know you guys are probably freaked out about Quicksort now that we saw this version versus like a nicer version, but we'll basically spend the full class on Thursday or Wednesday to go over that. If you just do it once at the beginning, then it's n log n and still n log n, right? So here's the issue though. You might think that solves it, but that's only going to solve it for that step. There's going to be the same situation again. That's like that's a constant. You're saying that now we've solved it from being potentially n squared to being n squared divided by 2. It's still going to be n squared. In the scenario here, suppose that we find the mean and we split it. That doesn't guarantee that the way things are split, we're going to have the worst case for the rest of it. So like, if we were to split this and we were to find the mean to be like 5 or whatever, I think 5 or 3 is the mean, probably 3. So we would have 1, 1, 2, and then 3, and then like 5, 8, 9, right? That would be ideal. But what if that is not the case? What if, actually, even if it is like that, that's really bad because, again, these are the edge cases, and then edge case again, edge case again. So that would be horrible in that case. So actually, a sorted list is going to be your worst enemy when it comes to Quicksort. That's the worst case. So you will see that it won't help you in the long term. It's just going to help you for the first iteration of Quicksort, but you're going to run into the same problem for the rest of them. So yeah, all right then. You are coding Quicksort for assignment 5 because the version that I'm going to show you on Thursday, that is actually the practical version of using Quicksort, does not involve any tree traversals at all. It is like 0 tree traversals related. Okay? This is just a visualization of Quicksort. The version on Thursday will not have any trees in it. So yeah. Like I said, it'll make more sense. But if I start out with that version, it's so mechanical that you might not understand how the splitting works, which is why I like this version. So I'll do another example of this version that's more balanced so you see it better, and then we'll go on to the actual mechanical version of that. So anyways, I think that went decent. So anything else? Thank you for coming. In that case, I will see you guys on Wednesday so we can complete Quicksort. I will go ahead and release the worksheet anyways. It's because you can start doing the other parts except for Quicksort. So that way you can have extra time. So, all right then. I'll see you guys on Wednesday. Stay safe out there.